Good evening. My name is Nikos Charalampidis, and today we will talk about the composition of fuzzy numbers with chaotic maps. First, we will start with an introduction, and then we will move to the problem formulation. After that, we will illustrate some of our results, and lastly, we will close this presentation with some conclusions. Fuzziness is a classic characteristic of speaking and thinking. As such, mathematicians decided to clarify this. The term fuzzy logic was introduced in 1965 by Lotfi Zadeh and is a generalization of the Boolean logic. It is an extension which allows values between the absolute true and absolute false to be characterized. The goal was simple: to quantify an information which is based on the lack of information or inaccurate data. For example, Nicholas is tall. In order to achieve the goal, the notion of fuzzy numbers was introduced. A fuzzy number is a generalization of a real number, and it is an extension where a single value is a set of possible values. For example, Nicholas can have a height of 179, 180, or even 2 meters. And each possible value is quantified between 0 and 1 around some reference point, where 0 corresponds to absolute false and 1 corresponds to absolute true. For example, consider the following trapezoidal fuzzy number with 4 reference points, of which 2 correspond to absolute true, meaning 1, and the other 2 correspond to absolute false, meaning 0. And assume that the domain of this trapezoidal fuzzy number corresponds to people's height. Then, from this diagram, we see that people with height between 171 and 173 belong in the same category. Also, the same applies for the people with height less or equal to 168 and the people with height larger or equal to 176. So the question arises: what happens with the people that are in between? Well, the answer is simple. Assume that the person has a height of 170. Then we will say that its height is equal to 171 with a truth index of 0.66 approximately. Similarly, if a person has a height of 175, then we will say that its height is equal to 173 with a truth index of 0.33. Moving forward, we will give now a more formal definition of the fuzzy numbers. From this diagram of the fuzzy number, we can say that fuzzy numbers should have at least one solution to be equal to 1. Also, they should be convex, meaning that it should not be wavy. And lastly, they should be continuous. The fuzzy logic finds its usefulness in various fields, and examples where fuzzy logic is applied to is like risk assessment methods for network security, autonomous robot navigation, rain and temperature prediction, performance evaluation of automobile fuel consumption, and many more. So we thought, why don't we try to use fuzzy logic and fuzzy numbers to our situation? One of our goals is to introduce new chaotic cryptographic systems, meaning that we want to use deterministic systems with extreme sensitivity to initial conditions and parameter value changes in order to produce random bit generators for encryption and decryption of an information, where the encryption key is the parameters and the initial conditions of our system. So in order to do that, first we need to introduce new chaotic systems. As such, the idea came pretty much smoothly. Given a one-dimensional chaotic map, we aim to establish a more complex chaotic behavior by modifying it with different fuzzy numbers. So we propose the composition of Gaussian fuzzy number and the generalized bell-shaped fuzzy number with the logistic map, Chebyshev map, and sign map, respectively. Indicatively, we will see the composition of the Gaussian fuzzy number with the Chebyshev map and the composition of the generalized bell-shaped fuzzy number with the logistic map. But first, let's see the definitions of the Gaussian fuzzy number and the generalized bell-shaped fuzzy numbers. The domain of the Gaussian fuzzy number is the real numbers, and it takes its values from 0 to 1. It's defined by this equation, and it's comprised by two parameters, sigma and mu, where mu defines the center of the fuzzy number along the x-axis. We can see it here on the right figure, and sigma specifies the shape of the curve on either sides of the central plateau, which we can see it here on the left figure. Similarly, the generalized bell-shaped fuzzy number is given by this equation, and it's comprised by three parameters, where the A parameter defines the width of the curve, as it can be seen here on the right figure. The B parameter determines the shape of the curve on both sides of the central plateau, and we can see that on the second left figure. And the C parameter specifies the center of the curve along the x-axis, and we can see it here on the first left figure. We're moving on to see a bit about the logistic map, which is a map, a chaotic map, it takes its values from 0 to 1, and it's comprised by one parameter that takes values from 0 to 4. Here below, we can see its bifurcation and Lyapunov exponent diagrams. Both of them are very well-known tools for studying the behavior of chaotic systems. The bifurcation diagram indicates for which values of the parameter the system exhibits chaotic or periodic behavior. Essentially, the bifurcation diagram is many simulations, one next to the other. For example, here, in the bifurcation diagram of the logistic map, we see that for r less than 1, the system asymptotically decays to 0. For values between 1 and 3, the system loses its stability, and for values larger than 3, follows a doubling period route to chaos. From the Lyapunov exponent diagram, we can validate what we see in the bifurcation diagram here, because it characterizes the rate of separation of infinitesimally closed trajectories. So if we see positive Lyapunov exponent values, like this here, then chaotic behavior is implied, which positive values we have here, and we also see here that we have chaos, so they match. Otherwise, if we don't have positive values, periodic behavior is implied. Now, taking the composition of the generalized bell-shaped fuzzy number with the logistic map, we introduce a new one-dimensional chaotic map, which is given by this equation. And it's comprised by 4 parameters which allow us to tune the behavior of our system. The first thing we can see from this bifurcation diagram, which is with respect to the R parameter, which originates from the logistic map, is that the R parameter now can take values larger than 4. Furthermore, similarly to the logistic map, in most cases, the system enters to chaos through a period doubling route. And in addition, it is easy to observe the phenomenon of crisis. A small windows here that you see white is the phenomenon of crisis, and meaning that the system exits suddenly out of chaos. But this is not all. Also, the system exhibits another interesting phenomenon, which we do not see in the classic logistic map, that of the coexisting attractors, meaning that for different initial conditions, but same parameter values, there are different regions of attraction for our system. For example, here in this bifurcation diagram, you see in the black, we used initial conditions to be 0.1. And with the red, we see that the system follows a different region of attraction to continue for initial conditions of 0.3. So now, if we choose the same parameters and also specify the parameter R to be around, let's say, 7.7, you can see here that the system for initial conditions of 0.1 has a completely different trajectory from when we use different initial condition, in this case 0.3. Also, it is worth noting that in many cases, this new map achieves a higher Lyapunov exponent than that of the classic logistic map, which is approximately 0.7. Next, in order to introduce the second new map, we must first tell a bit about the Chebyshev map, which takes its values from -1 to 1, and it's comprised by, again, one parameter, Z. The Chebyshev map, as we can see from the bifurcation and the Lyapunov exponent diagrams, for Z larger than 1, exhibits constant chaos. Now, the resulted one-dimensional chaotic map from the composition of the Gaussian fuzzy number with the Chebyshev map is given by this equation, and with three parameters to allow us to tune its behavior. On the left figure here, we see the bifurcation diagram of the system with respect to the parameter Z, and compared to the classic Chebyshev map, the proposed system enters to chaos through a period doubling route. Also, the phenomenon of crisis arise, and as the parameter Z takes larger values, the crisis windows become smaller. On the right figure here, you can see the corresponding Lyapunov exponent diagram, which confirms the aforementioned dynamical behavior. Here, you can see for the same system, but different now different choice of bifurcation parameter. We see the bifurcation diagram with respect to parameter mu, and we see that a new phenomena arise, like the phenomenon of antimonotonicity. You can see here where the system enters to chaos through a doubling period route and exits with a reverse one. You can see the phenomenon of hysteresis also, where the system exhibits sudden jumps. You can see it right here. Also, the small bubble here, which is in a antimonotonicity phenomenon too. And right here, the corresponding Lyapunov exponent diagram. It's worth to be noted that unlike the classic Chebyshev map, the Gaussian fuzzy Chebyshev map exhibits also the phenomenon of coexisting attractors. Now, because the Gaussian fuzzy Chebyshev map is comprised by many parameters, in order to better understand its behavior and in which regions chaos can be found, we have used Lyapunov exponent diagrams with respect to two parameters, where the blue color indicates regions with chaos and the red indicate regions where the behavior is periodic. Here on the left, you can see the Lyapunov exponent diagram with respect to sigma and mu, and on the right, the Lyapunov exponent diagram with respect to sigma and r. To conclude, we looked at fuzzy numbers and how they can be useful in introducing new chaotic systems. We introduced two new chaotic systems, and for future research, it can be to compose different fuzzy numbers with one-dimensional chaotic maps, and also to construct and modify higher dimension chaotic maps. In addition, these maps can be applied to the problem of random bit generation. Here you can see a bibliography. Thank you very much. Your questions.